The contents of our presentation is shown here. First we will give a background and introduction and then focus on the technology basis of the simulation systems, and then present the total life cycle drilling simulation system consisting of planning, training and real-time operation applications. And then we will look at some cases where our systems have been used, and finally give some conclusions. I will start this presentation to present a vision for drilling simulation. And this is kind of my own vision for the ultimate downhole drilling simulator. And such a simulator needs to represent the real physics of the downhole drilling process, and comprising an integrated drilling simulator which models all the relevant drilling sub-processes. Also comprising a transient flow model with both single and multi-phase capabilities. This flow model being coupled to a transient thermal Wellbore model, calculating the energy transfer in the Wellbore and the surroundings. Also incorporating drill string and vibrational model. Further on, a rate of penetration model interacting with the mechanical earth model and mechanical earth data. And finally, the mechanical earth model itself, which needs to include then 3D geological, 3D geomechanical and 3D reservoir models. These integrated drilling simulator also should be visualized in 3D in a virtual reality system, so that you can have a look on what is really going on downhole in the wellbore. Furthermore, my vision is to have this integrated drilling simulator enabled for planning, for training of personnel, for real-time operations and for review of operations after they have been finished. So that this system is coupled together in a total life cycle drilling simulation system. And the end objective or end vision is to utilize also this simulator for automation of the full drilling process, also coupling it to the drilling equipment. I like to look on the downhole drilling simulation from a historical perspective, and I'm going back quite some years. In fact, the first complex downhole drilling simulators, or maybe not that complex at that time, but they were pioneers for its time. They were emerged in the late 1960s. And this activity was pioneered by Amoco, the oil company which is now part of BP. And the key person there was Keith Milheim. He was leading the initiative in Amoco. And Amoco combined modeling and simulations with quite extensive experiments in their research labs. I also want you to see one example of a simulator called WellSim Drilling Simulator, which was in fact developed just before 1980. And you see a picture of this here. And here you can see how a simulator, which is far from as complex as today's models, but how that looked like. It was quite a comprehensive setup, and not as fast as today, of course. Along the years, there were a number of PhD projects which developed academic drilling simulators on several universities, Texas A&M, University of Texas, LSU, and so on. Then, throughout the 1980s and 90s, several R&D and industry groups took the work further. Amoco, they continued their efforts. In Norway, Rogaland Research developed several Wellbore simulators funded by the industry in joint industry projects, and also utilized extensive experiments on the Ulrig wells and the Ulrig facilities for gathering data for verification of these advanced simulators. In 1985, the first two dynamic kick simulators were published in SPE papers, and Henry Nickens published a dynamic model developed as part of the AMOCO initiative. This was first published in 1985 and then in the SP Journal in 87. And then Ekan and Rommetveit, we published a simulator for gas kick in oil-based drilling muds at the same conference in 1985 in Las Vegas. BP also had a large effort for simulations, and internally in BP they developed what they called a Wellbore fluids model. This was not the multiphase model, but it was focusing on the Wellbore fluids, hydraulics, transport properties. In Schlumberger, in their Cambridge research facilities, they also developed a transient well control simulator and combined this with experiments. SINTEF in Norway, SINTEF and IFE, they developed Olga, the Olga model, focusing on multiphase flow in flow lines, but also they have been also moving towards the wells. To continue this, in the beginning, drilling simulators were only used by experts for planning very special and challenging wells, and then after an incident had happened, incidents like kicks, blowouts, lost circulation and so on, they were not used as part of the normal operation. Around the year 2000, some projects were initiated at Rolv Research and at SINTEF in Norway to develop simulation systems which were linked to the real-time drilling process and driven by the real-time drilling data for the purpose of developing decision support system as well as drilling automation. And these systems have matured. Around 2008, in eDrilling, we demonstrated and have developed the eDrilling system, which is now called wallAhead, including also a 3D dynamic downhole visualization of the wellbore. A new milestone was reached when, in 2010, the downhole simulator in eDrilling called Intellectus was linked together with an advanced drilling topside simulator, iDrill, so that you had a combined topside and downhole drilling simulator for training. In 2013, the first lifecycle drilling simulation system with seamless transfer of simulated well states between the different simulators for planning, training and real-time was a reality. And from 2013 and onwards, the concept of the lifecycle drilling simulation concept has been growing in the industry and is growing. And I'd like to finalize this historical perspective just by showing you here in this figure the WellSim Interact Engineering Drilling Simulator of 2015. It has the same name as the one shown on the previous slide, but here you have the 3D wellbore real-time visualization. You have a control screen or panel where the engineer can control the operation, and you also can use this for quite fancy processes, visualizing seismics and also logs during operation or during simulation. I'll also briefly like to go through the history of the eDrilling products. And the eDrilling company and products started out of the R&D, the research, ongoing research in SINTEF. And in 2004, the eDrilling project was started to develop the eDrilling, now called wallAhead, the real-time simulation and decision support system. This was demonstrated around 2008 by Total and ConocoPhillips, and a prototype was ready. Around 2010, Statoil came in and supported the development of the big transient training simulator, also incorporating the topside. Moving ahead, the lifecycle drilling simulation was set up in 2013 in China in cooperation with CNOOC. In 2014 we had a large agreement with Chevron, and ConocoPhillips have been continuing to support the development. Also now on incorporating integrated construction and engineering simulator into their facilities in Norway at Ekofisk. We also have had some very extensive training activities. Now more than 3,000 drillers and well engineers have been trained in the advanced training facility in Norway and elsewhere. Now in 2015 and moving into 2016, our company is expanding. We have set up offices in Houston and recently in Singapore. And we are, together with our customers and partners, moving ahead into the future. I'll go a little bit more into the technology. This slide shows schematically how the integrated drilling and well simulator, what component it has. And the core, the heart, is the flow model. The hydraulics and integrated with temperature modeling, and this interacts with torque drag model, with wellbore stability model, with rate of penetration model and pore pressure model, and the mechanical earth data is linked to this model, both when you set it up, but during real-time operation the updated mechanical earth data can also be taken into account in the modeling. This integrated simulator is then utilized towards the boxes below, which represent a schematic picture of a sub-operation in drilling, completion, intervention, and so on. So special applications have been developed in order to facilitate utilizing the simulator in all these operations. Just to show you the complexity of the simulations, here we have the flow model, and this handles all the complexities of the drilling mud properties, the mud compositions, all the different fluids, the densities as a function of pressure, temperature, and component, and the temperature, thermophysical properties. In the case of an influx, the model takes care of this, the dynamic reservoir influx model, the gas dissolution in oil-based mud, phase and PVT properties of the mixture in the vertical base and the multiphase flow. All this is taken into account. There are also additional elements which can be taken into account in special studies, but these are not part of the real-time and modeling. The next key technology is the pore pressure module, which also has been developed in SINTEF throughout long extended research. And this takes care of the development of the pressure in the formation through historical time, and it models the lateral flow of fluids, the shale compaction, the port cementation, the hydraulic leakage, the vertical and minimal horizontal stresses, and so that a pressure distribution of the basin where we're going to drill into is then computed based on historical geological development. And this software is then used to model the pore pressure distribution along and around the planned well. And when we link this up to our real-time system, we then first make a pre-study and make some pre-drill predictions based on Monte Carlo simulations. This is the profile here. This is the pre-drill prediction. During drilling, logs and updated data are utilized in order to, of course, update this profile, so that in the operation we can, while drilling, update the prediction ahead of the bit and have a more accurate prediction of the pore pressures. Also, in the wellbore stability domain, we have utilized a model developed by SINTEF in our system. And this can be linked into the system by the users. And in this model, the system models the fracture gradient and the collapse gradient for the system which is being looked at. And when we are utilizing this in real time and linking this to our wellAhead system, the data from wellAhead is then entered into the pre-processing unit of the Wellbore stability model. In addition, stresses and strengths and data from the operation, from logs and so on, are utilized. And a recalculation of the wellbore stability is performed, so that new probability profiles for collapse and mud losses and so on are calculated and entered into the real-time system. Now the next key element is the virtual wellbore, which is a combination of all the advanced mathematical models, the integrated drilling simulator, and the virtual well visualization. The results of the simulations can then be visualized in the real downhole wellbore environment. And you see an example of this here. And when we put all this together, we have utilized the downhole drilling simulator, the integrated drilling simulator, in the whole life cycle drilling simulation systems, from planning, where we can do what-if evaluations, dynamic planning and post-well analysis, to training, where we can do training of the full drilling teams, testing of new technology, procedure verification, but also interactive drill well on simulator engineering and testing the technical limits. In real time, the real-time models are then driven by the drilling data. We are doing look ahead or automatic forward looking. We can do what if evaluations, and the system gives decision support in form of warnings and diagnostics. And both the training simulator, the drilling simulator, and the real-time system is linked to the advanced 3D downhole visualization. Some more details about the products themselves. I will not go into any details. This is listed in the handouts you will get via the internet. But just to say that the well planner, the planning system, is a suite of applications focusing on dynamic, advanced evaluations prior to drilling a well. Then we move over to the real-time system called wellAhead, and this when we run this system, the simulation is driven by the drilling data themselves and the operation itself, and this is linked to the dynamic 3D virtual wellbore, and you see some examples of that here. There are also some replay functionalities in this system, so that you can also replay an operation afterwards. Features of the wellAhead are that it gives automatic warnings and diagnostic messages, automatic drag charts, compares stress versus yield, and you can also compare simulated versus real-time data if you want to verify the diagnostics and warnings. So to summarize the wellAhead, this has demonstrated to be a very proactive system and not reactive. It gives an automatic supervision of the drilling window. You can automatically update the pore and wellbore stability during drilling, and you can also during operation get diagnostics and warnings on important characteristics down in the wellbore, which has impact on both safety and technical quality of the well. In addition, automatically the system gives a forward looking of the downhole ECD and the torque drag for the next drilling period, and it has, you could say, capabilities to be a virtual downhole pressure while drilling sensor, which is a virtual sensor because it calculates the downhole pressures, but it really gives very good calculations. And here we see some examples of screen pictures, 2D plotting here, the examples of the 3D on the top here, and we have also two other examples of how the 3D virtual well can look like. This real-time system is quite unique. In the bottom it has verified dynamic models. It's linked to 3D downhole visualization, and also the models are linked and visualized in this visualization. As I mentioned, it has automatic look-ahead capabilities. On the fly, you can also do what-if simulations by extracting the calibrated model out of the system and do your own what-if evaluations. It does dynamic modeling of the operation in all the transient phases. And it also provides integration between dynamic planning, real-time operation and the simulator systems which are available in the life cycle drilling simulation system. This slide just shows you and gives you a lot of details about the large training simulator, this is used for training of drilling personnel, and here you see we have linked an advanced topside rig simulator from Oiltech Solutions, the iDrill, together with the WellSim, which is the advanced downhole simulator. And on this simulator you can train on your own well, so to say, and you get very realistic feedback from the wellbore. We have developed an engineering version of the WellSim, which we call WellSim Interact. And this is an interactive simulator, and here we have a very simplified engineering topside so that the engineers themselves can sit and control the drilling interactively. Apart from the control side, all the other elements are very similar to the large training simulator, but this is especially focusing on engineering, on training of engineers, and also on testing the technical limits in the well you're going to drill. Now we will move from technology and the products over to some cases where the products have been used. First we have the Martin Linge pilot. And the Martin Linge pilot was performed as a kind of prototype demonstration of the wellAhead system. And in this case, we first tested it on an advanced well, which was drilled prior to the Hild well. Then we did a lot of pre-modeling work in order to be ready to do pore pressure and wellbore stability updates during the operation. And during the operation, we did a real-time modeling of ECD, pore pressures, and wellbore stabilities. And this is an example just showing how the system functioned regarding calculation of ECD. Here we have in blue, this is the calculated ECDs. And in pink, this is the ECDs measured by the downhole sensors. And you see, when the downhole sensors did not function, the model functioned very well. And when the downhole sensor came back, it was spot on what was modeled. So in reality, it shows that the downhole modeling can be used for some periods if the downhole pressure sensors falls out and doesn't function. And then you can avoid to pull out of hole, for example. To summarize the value of using the eDrilling system on this well, this was summarized extensively together with the Total in a report and also in a paper. And to summarize this, approximately 2 weeks of rig time could have been saved. And also a lot of materials, mud, we could have avoided mud losses and maybe avoided the squeeze cement jobs. So altogether, the potential of using eDrilling on this well could have been very high. However, Total chose here to run this as a pilot. So they ran their traditional methods, and alongside with that, they ran the full eDrilling system. But they used their normal procedures in the well establishment. This is documented in a paper.
Okay, this slide takes us to China, to CNOOC, where we see the setup for training, planning, and support center in Tianjin, China. It's a large curved screen with 2 driller chairs with feeder-like seats behind, which is all part of the training simulator for offshore personnel and drilling supervisors. Another room is basically equipped with a simulator and real-time operation software. And the way it's been used at CNOOC, when the personnel received wells, they would normally follow them with the wellAhead and support them 24/7 with support from 3D visualization. At the same time, another group of engineers would focus on planning and optimization and would support those currently monitor wells, and also would be handling requests from drilling supervisors. At the same time, the team of supervisors and offshore personnel would be trained on a high drill. But now, since CNOOC showed interest in the new product WellSim Interact, they would like to integrate it into their system and the complete well life cycle simulation. Yeah, that's all from me. Thanks.
We also have a very good experience in cooperation with Wintershall on the IMSA well, where we partner with Maersk Training in order to use our products and to do support for Wintershall in this operation. And just to summarize this, in the evaluation afterwards, Wintershall have estimated that they saved 19 days compared to a standard operation due to utilization of the eDrilling models and the support from the personnel of eDrilling and Maersk Training. So it was a very good result. There will be some papers documenting this next year, published in the SPE environment. Now coming back to the vision again, and I want to revisit this before I go to the conclusion. The same vision which I started the presentation with, and try to conclude then that the first point, the advanced downhole drilling simulators have come a long way from R&D and expert tools in the 1980s to today being integrated in operational support and automation. So the vision is approaching, and it's realistic to reach. Life cycle drilling simulation systems is today utilized by major oil and gas players around the world to reduce cost and improve safety during well construction. Real-time data-driven modeling and decision support has been used with good results in challenging drilling operations, and significant savings and reductions in NPT have been achieved and can be achieved by continuing to use this. And finally, to combine transient modeling in the whole life cycle of well construction, from planning through training, real-time operation and lesson learned, can generate lower costs and increase safety. So with that, the presentation is finalized.
Okay, so we have gone over our time, unfortunately. But if there is any questions, we will take our time to answer those. And we already have a couple of ones. So the first question, is the flow model for influx two-phase flow similar to Olga for kick simulations?
First of all, the Olga model does not simulate, is not used as a kick simulator as such. Olga model has been used mostly for production, for multi-phase transport in flow lines, but also for multi-phase flow in wells. The model in Olga is somewhat more detailed than the model in our kick simulator. In our kick simulator, we utilize so-called drift flux approach, but in the Olga, it is they are modeling the interaction between the phases more in detail. For non-Newtonian fluids, I think it will be unrealistic to have good models of the level of the Olga model.
Okay, another question. Can you say something about how the automatic warnings and messages are presented and made use of in practice?
I'm glad to have this question because the ultimate goal, of course, is to have automated diagnostics of problems. We have been using this, but when we present this for the oil company users, we are holding these back somewhat until we are very sure that the conclusions from this diagnostic system is correct. When you're dealing with operations and operational people, I think there's only one or two error messages, then they will lose the faith in the system. So the way we use this, we use it internally, the automatic messages, but then we choose if we're gonna publicize this to the operations.
Okay, can you elaborate on solids effect on ECD, cuttings carrying, hole cleaning capacity, particle settling, etc., both technical and commercial?
Yeah. I don't think the time allows to elaborate in detail on this, but our models handle the solids and the transport of the solids. And the cuttings is handled as a separate phase in the multi-phase flow equations and transported as a separate phase. We utilize equation for cuttings slip and transport, and we then clearly see the effects on the ECD of the cuttings. For instance, if you change your drilling rate, if you increase that, then you will have an increased cutting concentration and you will have an increased ECD downhole, which is very important, for instance, especially for deep water wells where there's been problems in this respect. We have this facility in our models, and we are also promoting this, but in our presentation today, our main focus was more on the ECD, the results related to the ECD calculations in our cases. Okay.
Okay. We got another question in. What is eDrilling recent relation to Chusov, and how does this affect business model offered to the market?
Well, eDrilling, there's been a change in ownership in eDrilling, and this is a quite natural process in a company like ours. And now Sintef shares were sold, and the big player, the other owner, which is then controlled by High-Tech Vision, came in and controlling the majority of shares currently. And TerraSoft is a subsidiary of High-Tech Vision. This does not affect very much the business model, but we have some modifications. One of them is that we will focus more on providing the best software to the customers and not have a high focus on developing our own service organization. But we want to provide the software to all the different users who want to utilize this for their own purposes.
Yeah, but we have also started having partners to deliver the service.
Yes,
yeah.
That's part of that strategy.
Yeah. So another question: are the oil companies able to host, control the content of automatic messages diagnostics? For example, provide their own risk library, or has this not been requested by oil companies?
The oil companies are able to control this, and if the oil companies acquire the system, then they will be trained in order to control the whole system themselves, and then learn how to utilize this. And we are training the companies who have acquired this system themselves to do this.
Yeah, but we can also import the risks that are known into the 3D visualization tools, so they can follow it into operation.